Okay, so now we are going to talk about another parameter of power grid systems, or state variable, which is frequency, and phase, which is very related to frequency. Um, so frequency uh, is, I think, a concept that everyone feels they understand well. And on the power grid, frequency corresponds physically to the rotation um, of large magnets in generators, synchronous generators that are powering the grid. Um, and so we can model this rotation as a sinusoidal function with a magnitude, and Mohini just covered voltage magnitude, and but there's also the argument of the sinusoid, and so here I'm breaking down that cosine argument into two terms, omega naught times t, which is omega naught being the nominal 60 hertz frequency on the grid, and then phi, which is the phase of this oscillation. Um, and it's important to understand that phase only has meaning when you're comparing two sinusoids. Um, so in this image, we can see that these two ideal sinusoids, cosine and sine, are separated by a phase phi of 90 degrees. And so, and we can visualize that in the phasor diagram um, on the bottom, in the bottom picture. However, this phase definition, this simple phase definition really is only meaningful and well-defined for ideal sinusoids with constant frequencies. And you can imagine asking yourself, what is phase for two sinusoids at different frequencies, where for every moment in time, it seems like the apparent phase between them is changing. So for that case, we will we'll add some complexity to our functional form of the voltage waveform, and allow the magnitude to vary with time, which Mohini illustrated in her talk with voltage sags. And we also will allow this phi term in the argument to vary with time. And then we can define the frequency as the time derivative of the argument of this cosine. And so in the bottom, we see that under that definition, the frequency would be omega naught, which is the 60 hertz nominal frequency, which is constant, plus this d phi over dt term, which actually does vary with time. And this d phi over dt gives us the all the complexity that we see in real data on the grid. We can also, what is often done is we subtract out the nominal frequency term, because since it's constant, it's not very interesting to us. And then we're just left with this phi of t term, and so we can then define the omega of t as the time varying frequency deviation from nominal. And so let's show some think about some examples of phase in different situations. So in this top row, um, we have time, like a waveform of a signal in time. And um, so it's remember that the phase needs to be defined between two sinusoids. So in this case, the reference sinusoid that we are using to define the phase is a perfect 60 hertz sine wave. So on the top row, our signal is also an ideal sine wave of 60 hertz. However, it is phase shifted from from our reference sinusoid. When we calculate phi of t, in this situation, we're going to get that it is non-zero but constant. And when we take the derivative of phi of t to obtain frequency, we're going to get that the frequency is zero. And this makes sense because what we really mean by omega is the frequency deviation from 60 hertz. So since our original signal is at 60 hertz, it makes sense that omega is zero. Now, in this bottom row, now our sinusoid signal that we're measuring is slightly, has a frequency that is not 60 hertz, but slightly larger than 60 hertz. And what we get from our definition of phi of t is that it is linearly changing with time because the frequency of our signal is constant, but different than 60 hertz. And so in that case, when we calculate the derivative of phi of t, we get a constant frequency that is greater than zero, which means that our frequency deviation from 60 hertz is greater than zero. So our actual frequency is slightly larger than 60 hertz. So now let's look at some real data. And so this data is from the Sunshine data set, which was mentioned earlier. And just visualizing what we see, we notice that the phase is constrained to be within 0 and 360 degrees. And this makes sense based on our sort of understanding of phase angle, where an angle is usually between 0 and 60 degrees. However, this creates some problems when we want to do computations using this phase, because let's say we want to actually take the derivative to obtain frequency. Part of that process is computing a discrete difference of phi of t. And we see in the bottom plot that this discrete difference has these very large artifacts that occur every time the phase jumps from 0 to 360 degrees. And so these artifacts are not physically large jumps in frequency, and so we need to remove them to see the actual frequency signal. And so to do that, we're going to unwrap the phase. And what that means is remembering that angles are relative. And so an angle of 0 is equivalent to an angle of 360. An angle of 10 degrees is equivalent to an angle of 370 degrees. And so when we see a zero crossing of the phase, we can add or subtract 360 degrees and still have the same angle, but remove the discontinuity that's present in the data. And so we can do this with a relatively simple function. And what this function is doing is it's assuming that these discontinuities in the phase are significantly larger than the other differences between consecutive points. Which is a good assumption looking at this plot of the like initial difference. We see that actually we can't see any variation around other than these large artifacts. So we define a threshold that is going to be between these discontinuity, the value of these discontinuities, which in this case, the value is going to be very close to 360 degrees. And so we can define a threshold that's maybe 350 or 300. And when we detect a change that is greater than our defined threshold, we assume that we've encountered a discontinuity and we either need to add or subtract 360 degrees to remove that discontinuity. So now we're going to use these tools that we've developed to look at a case study, which is the Blue Cut fire, which happened in 2016, August 16th, 2016, in Southern California, and it caused a transmission line fault, which caused a drop in frequency that caused large solar farm inverters to trip offline. And so looking at our sunshine data set, we see that we do have data on this day. So that's exciting, and let's check it out. Let's look and see what we find. I've gone through all the steps that have been talked about earlier on, like how to query the database and obtain this data. And then I've unwrapped the phase so that we see this continuous phase evolving. And then now we can take a derivative and we get this graph of frequency. And there's a few things to notice. The frequency displayed in this report of the case study, of the report of the Blue Cut fire fault, looks very different than this frequency initially, and we'll like explore that. Another thing to note is that what isn't apparent, or taking the derivative to obtain frequency, has introduced a lot of high frequencies in the outputs, which weren't completely apparent in the phase plot. So a very common method to deal with this introduction of high frequencies is to use a low pass filter. to get a better signal. And so here we are with the same plot of frequency, just visualizing a part of it during nominal functionality. Zooming in, we see that the frequency is just under 60 hertz, and it's varying quite a bit. And let's zoom into this large spike, which is due to the blue cut fire fault. And we see that a few interesting things. So this graph is actually plotting 4 different PMUs at different locations on a distribution network. And we see that these PMUs disagree on what the frequency is during this anomaly. We also see that there's overshoot in the frequency signal. And this overshoot occurs at a very short time scale. The time scale much shorter than like you would see from an actual controller that is controlling the generators that are actually causing the frequency. So that those 2 facts lead us to believe that we are seeing some errors or artifacts in the that's coming from the signal processing internal to the PMUs themselves. So here we're just visualizing on the bottom the graph that's reported of the frequency faults during the blue cut fire, and our data, which they look quite different. So what we're going to try to do is apply a low pass filter, specifically a moving average filter, to smooth out this high frequency noise that's been introduced by taking the frequency. And so to introduce the concept, or to explain the concept of a moving average filter, let's look at maybe some plots that many of you have seen following the news. And we see here is from the New York Times, a graph of daily COVID cases. And we see that on a day-to-day basis, there's quite a lot of variation, but you can take a 7-day average and get like a smoother line. So we're going to do something very similar to that, but it's not going to be on the scale of days, it's going to be on the scale of seconds. And so here we are applying 2 filters, 2 moving average filters to our data. And if our window length is about is exactly 0.1 seconds or 100 milliseconds, we see that that doesn't provide very much filtering, and our data looks very similar to the raw data. But if we apply a 0.5 second average to our data, we lose the overshoot that we're seeing in the first plot, which is promising because that overshoot is likely not due to a physical process. And we also see that after applying this filter, our data now resembles the frequency data reported from the blue cut fire. So I think this is a this is a very exciting case study that shows that um, this data um, is, well, real, uh, and that it illustrates that frequency is largely a global variable across the grid. So even though these PMUs on the sunshine data set are at different locations, they're all reporting a very similar frequency trend um, that agrees with um, the frequency from this fault. And so a few conclusions. Another point is that frequency is not really well defined during transient events, because during these transient events, the waveform isn't really sinusoidal for a brief period of time. And the PMUs are, ingesting point-on-wave data and fitting that data to sinusoidal function, which works well when the point-on-wave data is about sinusoidal or nearly sinusoidal. But during these fault events, that fitting algorithm is now operating under, or the assumptions it's operating with are being temporarily violated. So there is likely going to be some frequency error during these transient events. There is an IEEE standard that requires PMUs to have errors within certain bounds, but the specific algorithm that these PMUs need to use is not specified, and these algorithms are often proprietary to the companies making the PMUs. So it's, I think, good to remind ourselves that point-on-wave data will be most accurate during these transient frequency events. And so that's all I have, and happy to answer any questions.